All right, guys. So today, going to talk about classification, um, and we'll also kind of recap what we didn't quite get to do at the end of last lecture as well. And then a few announcements. So vitamin 35 due Friday. Again, because people have been having issues with internet being lost and stuff like that, we're going to make homework 11 due on Saturday now. So 1 day extension, and then same for the project 3 checkpoint as well. So I'll give you guys an extra day for that. Um, Hopefully all the issues don't stop you from submitting on time now. And yeah, the homework 11 early submission deadline is also moved. So now you turn it on Friday. Is that right? Yeah, for a bonus point. So yeah, cool. All right. So now to kind of recap the last few slides that we went over last time. We didn't quite get to go over the demo, so I want to make sure we get to do that. So we were talking about the true slope, and so we kind of arrived to that point in the lecture by building the intuition that, like, if you wanted to see the variability of some part of your regression line, you could do this by bootstrapping. So for example, if you wanted to predict the y value for a particular x value, you just go to that point on the line, like find that value of x, shoot it up to the line, that's your prediction for y. And then if you want to see the variability of that prediction, you could bootstrap your scatter plot, fit a line to every single scatter plot that you bootstrap, and then look at the predictions in each of those bootstrapped regression lines. And then you'd be able to see kind of how that y prediction varies. So that was like one example that we talked about using bootstrapping in the context of a regression line. And one thing I wanted to also clarify about that is that you're predicting this interval for the prediction. It's like a confidence interval for the prediction, but that's not really a confidence interval around what the value of a new person is actually going to be. Because as you saw in the scatter plot, the actual y values like vary quite a bit. So that's not saying that that's a confidence interval around where that person is actually going to be. It's actually just a confidence interval around the true y value on that true line. Remember, this is like true line that we're assuming exists in the natural world. And so you're really making an interval for the location of y at x on the true line. The variability of some new person who comes in who has like an x value is probably going to be more than that. The variability of just the y value at the line. So that's one distinction I just wanted to make really clear there. Um, and so the idea is you could use the similar, pretty much the same exact technique to create a confidence interval for the true slope. So there's many times where, if you have a scatter plot of two different variables, you actually care about the slope. The slope means something. There's like some meaning there. For example, if you're tracking like the distance of some object like over time using like some sensors, um, and you wanted to know the velocity of this object right now, you might plot like a bunch of different distances over time. And so the slope of that line would actually give you the velocity. So as an example where the slope of a scatter plot actually means something interesting that you care about. And so if you wanted to create a confidence interval for the true slope, then you could follow a similar process. So bootstrap the scatter plot, find the slope of the regression line through every single bootstrap plot, repeat that process multiple times, and then you just draw an empirical histogram of the slopes. So take the slopes from all the bootstrap scatter plots, and then make a histogram of that, and then just take the middle 95% interval. And so this is a way to create an approximate 95% interval for the actual slope of the line. So let's take a look at this in the actual demo. So I'm going to read back in that same table that we were looking at last time, which is like all of the babies who were born and their mothers. And so we're going to look at gestational days and birth weight once again. So we have gestational days on the x-axis, birth weight on the y-axis. And so we have the scatter plot here. We fit a regression line through this. And then the slope of this line um, down here is 0.5378. And so if we wanted to create a confidence interval for the true slope, because there's maybe, we assume there's some true relationship, some true slope between these two, then we can do this using bootstrapping. So we've created a function here called bootstrap slope, which will let you do that. So you basically pass in your table, the column for x, the column for y, and then how many repetitions you want to do in your bootstrapping. And then it's going to basically do those steps for us. So the first thing it's going to do is it's going to bootstrap the scatter plot, find the slope in that particular bootstrap, and then append it to this array of slopes. So this is going to allow us to actually get like all the slopes. Then what we're going to do is once we have all the slopes from all of our bootstraps, we just find the 2.5th percentile, 97.5th percentile. So that gives us the middle 95%. And then we look at kind of what was the observed slope. So it's kind of like the actual slope we got in our original sample. And then we'll just kind of display the results all together. So we'll display kind of the observed slope from our sample along with that 95% confidence interval generated from the bootstraps. So that's what that function is going to do. So let's actually run it. And we'll do a sample size of 2,500 in every single bootstrap sample, because we have quite a lot of data here. So we can, every time we resample, we can do quite a large sample size. And so here we get that, once again, the actual slope of the regression line in our particular sample was 0.5378. And then through bootstrapping, this was the variability that we saw in the slope. So sometimes it gets as low as like 0.45, sometimes it gets as high as 0.62. And in the middle 95% confidence interval is going to be these two values here. So from 0.458 up to 0.621. So that's how we can do that. So I just want to answer one question here. What's the significance of finding the true slope? Is it that it gives us information about the rate of things? Yeah, so that was just a particular example. So slopes slopes in general, slope is a rate of change typically. So if you have like time as your x variable and something else on the y-axis, then you could actually try, the slope would mean like the rate of change of that particular thing over time. But that's not always the case. Like in this case, right, we're looking at gestational days and birth weight. So in that case, how would you interpret the slope? So it's kind of like for every additional gestational day, how much heavier should the baby be? That's kind of how you would interpret the slope. So for like each 1 unit change, how much does the other variable go up? And so that's how you can kind of interpret what the slope is. So in this particular case, what it's saying is that if the baby is in the womb for 1 day longer, they're expected to be 0.53 ounces heavier. So that's how we would interpret it here. So that type of quantity, that rate of change, is very useful in many cases, many applications, like economics, like politics, whatever, like even biology, physics. So it's used all over the place, but it's just contextual. Depends on like your particular problem and the variables you're looking at. Cool. So that's how we can make a confidence interval for the true slope. So if we wanted to know like kind of where we think the true slope might be, this might be one way to do that. And so another way that this is useful is to assess whether something actually even has a slope to begin with. Like, does it actually have a slope, or are these two variables just like zero slope, zero correlation? And so we went over this slide last time, so I'll just go over it kind of quickly again. But basically the idea is, when you go out in the real world and you actually observe data, the chance of actually getting like a slope of 0 is like almost 0. Like you would need to have your data like perfectly 0 correlated. So you're actually never going to see a slope of 0 in the real world. Like if you do, let me know. Yeah, I don't think you actually ever will see it in the real world. You're going to probably see things like they're close to 0, but you'll never actually see 0. And so the idea is the reason you're not seeing 0 is because there's noise, right? There's variability. Every single time we take the scatter plot, we get slightly different data. Every time you sample, you get slightly different data. And so the idea is that just by chance, you might have gotten a slightly positive slope. If you do it again, maybe you get a slightly negative slope, in which case the slope probably isn't 0. It's just kind of noise. So to kind of show you that, we're going to go back to this function that we created and we used last time in lecture called draw and compare. So if you remember this function, let's just basically generate data from some true regression line. So you specify the slope as the first argument, the intercept as a second argument, and then the amount of data you want to generate. So this was the thing that we did at the beginning of last lecture where we said like, oh, let's take something that has like a slope of 5 and an intercept of -10, and let's generate some data from it and see what that would look like. So what we can do here is we can try this with a regression line that has no slope. So we're going to do a regression line that has a slope of 0, and then it has an intercept of 10. So it's just a flat line at y equals 10. And let's generate 25 data points from that. So let's see what happens when we do this. So here we have our green line. This is kind of the true line underneath. And then these are the points that are generated from that using this function. And what you would actually see in the real world if you saw this data is you would just see these points. So you wouldn't get to see that green line. You would just see these points. And then what you do is once you see these points, you'd fit a regression line to them. So in this case, the regression line happens to look like this, which is actually quite negative. And so now if you compare the regression line that you got on the data versus the true line that the data was generated from, you get quite a difference there. And so it seems like if you didn't know what this green line was underneath, you might think like, oh wow, there actually is some kind of a trend here. There is a negative association between these two variables. And so that's kind of just showing you that even if the true line is completely flat, when you generate data randomly from it, because of the randomness, you're probably going to get some slope that's not zero. But that doesn't mean that the slope is not zero. You have to be careful there. And this is a good example of that. And so how do we actually assess whether that true slope underneath is not actually zero? And so the way we could do this is that we could do a hypothesis test. So the way we'll do the hypothesis test is we're going to say the null hypothesis is that the slope of the true line equals zero. And then the alternative is going to be that the slope is not zero. So it's like something non-zero. And the way that we're going to simulate from the null hypothesis is that, well, if the slope of the true line is zero, then we can just kind of bootstrap our data, and we should be able to get a sense of like how the slope varies by just bootstrapping. And then if it is zero, then we should see that like sometimes the slope is positive, sometimes it's negative. If it's not actually zero, we should see that all the time the slope is positive, or for example, all the time the slope is negative. So that's one way to kind of assess that. And so let's actually go through and do this. So let's take another set of variables, for example. So let's take maternal age and birth weight. So this is the age of the mom and the weight of the baby. So intuitively, you're probably thinking like these should have no relationship whatsoever. It doesn't matter if the mom's like 25 or like 28, like birth weight really shouldn't matter here. And so the slope of these, if you look at the scatter plot of these two, they actually do have a positive slope. There's a slope of like 0.095. Now this is quite small, it's like almost zero, but it is not equal to zero. And so then the question is this just due to chance? Did we just happen to sample a set of babies and women such that like when the slightly heavier moms have slightly heavier babies, like is that just by chance or is that just like noise? And so how can we assess that? We can bootstrap to do this. So first of all, just to show you the data, this is actually what the scatter plot looks like. So as you can see, it looks like there's not too much of a relationship here. Just pretty much just looks like noise. But we are getting a positive slope. And so that slope could be real, but we need to understand whether it actually is or not. And so how do we do this? We can bootstrap. So we'll do the same thing again here. We'll call this bootstrap slope function, pass in our data, and then our sample size is 2,500. And might take some time to run here, but should tell us kind of the result. Here we go. So again, the slope that we actually observed was 0.095. We resampled our scatter plot many, many times, fit a regression line to every single scatter plot, and then now we are plotting the slope from every single regression line that we fit. And so in this case, we see that sometimes when we resampled our data, we got a slope as low as negative 0.2, but sometimes it's as high as 0.4. But the main thing here is that if you create that middle 95% confidence interval, then we see that it's below zero. The left end is below zero, the right end is above zero. So it actually contains zero. And so in this case, if you were using like a 5% cutoff for your p-value, then you could say that, you know, the data is more consistent with the alternative, or sorry, more consistent with the null, that the slope is zero in this particular case. We basically don't seem to have enough evidence to really say that the slope is not zero. So again, the slope of the regression line was non-zero, but then when we bootstrapped, we saw that, well, the slope actually jumps around so much when we bootstrap that means that it's probably just noise. We just happened to get a sample that gave us a positive slope. When in actuality, the slope probably is zero. So any questions about that, and like that process that we just went through? So seeing some questions about residual plots, but just wanted to make sure if there's any questions about this process specifically. I'll get to those though. Oh, someone said, are we not doing p-value? Like, are we not assessing the p-value here? So if you wanted, you could calculate like a p-value as well. But what we're doing here is we talked about how you can just use a 95% confidence interval that's equivalent to like calculating the p-value. So in this case, we're going to just calculate a confidence interval for where the slope must lie. And then if the null value is inside the confidence interval, then we say the data is more consistent with the null. Otherwise, it's more consistent with the alternative. Another question, someone said, the slope of the regression we observe is not the true slope. That's correct. In general, the slope you observe from your scatter plot is an estimate of the true slope. You'll never actually know the true slope, but you can try to estimate it. And so in this particular case, the estimate was really close to 0. And it could have been that the true line is non-zero, but from bootstrapping, it seems like probably the true line is 0. Are we finding the slope of the regression line to assess whether there's a correlation? Yeah, that's one way you could look at it. So this is one way to assess whether there's a linear correlation between two variables. So again, it's possible that you can have a correlation of like 0 and linearly, but there's a non-linear relationship. So that's really important to keep in mind as well. So this is all in the context of linear. This is a very, very specific like case of relationship between two variables. We're assuming something quite strong here, that there's a linear relationship between them, meaning that it looks like a line rather than like a curve or anything like that. Cool. All right, so let's just recap that basically. So if you want to test whether there really is a slope, this is kind of the setup. So null hypothesis is usually the specific one that you can simulate from. In this case, we're going to say the slope of the true line is 0. And then our alternative is that no, it's not. And then how do we actually assess this? We construct a bootstrap confidence interval for the true slope. If the interval doesn't contain 0, the data is more consistent with the alternative. If the interval does contain 0, the data is more consistent with the null. And so someone said, well, couldn't the true slope be one of the other values in the interval? Like maybe it could have been like 0.01 or something like that. It's definitely true. It could be, but we're just kind of taking that chance. That's not that, when we say that 5% cutoff, that's kind of what we're saying is basically like, that's the chance we're taking. Like, there's a 5% chance that we would still reject the alternative or the null, even if it is true. Like that's just something that we're going to accept. We're not, hypothesis tests aren't perfect, but the idea is, you can be like fair. The data seems to be more consistent. If you had to choose between these two, the data is more consistent with the first one. That's basically the idea here. You would kind of need to have, if you really wanted to claim that it was like some value, like a little bit bigger than 0, you'd probably want to have your interval be like really tight around that value and like not include 0. Then you could be like a lot more confident in saying that, okay, actually it's not 0. But given that the interval is really wide and contains 0, it's hard to make that kind of a claim. Cool. All right, so now let's get on to classification. And so I guess let me just go over really quickly prediction. And I think we've talked about this earlier in the course as well. But the basic idea is, in statistics at least, or in data science, prediction is about guessing the value of some attribute based on incomplete information. And so it's not necessarily about like predicting something in the future or anything like that. Like that's not really what prediction means. Prediction just means trying to guess the value of an attribute based on incomplete information. And so one way to make predictions, for example, is, if you want to predict an outcome for some individual who you don't know everything about them, you know some things about them, but you don't know everything about them. What you can do is the attributes that you do know about them, find other people who are similar to that individual, at least on those attributes, and then whose individuals you know what their outcome is, and therefore you can use those outcomes as a good way to predict. And so this is essentially what a regression line already does. A regression line basically says, okay, let's look at like things that have a similar X value to you. That's going to be what our Y value prediction is for you. Whatever Y values they have, that's our prediction. So, it's a thing that we've already been doing. And there's two kinds of prediction essentially. So one is regression, which is when you're trying to predict something numeric. The other is classification, which is what we're going to do now, which is predicting something that's a category. So that's the only difference actually between these two. So regression just means I'm predicting some kind of numeric attribute, such as the weight of a baby, whereas classification is something that can only be a category. So for example, if you want to predict like whether a baby is like premature or not, or something like that, then that would be classification, because that'd be a category. So that's the only difference here. But the difference is really small, but actually it's so big in the sense that the techniques we're going to use to do these are very different. So this concept of like fitting a line through your data, it only makes sense in numeric case. It's not something we do in categorical. So we're going to have a slightly different way of predicting things that are categorical. And so to give you a sense of like some additional like concrete examples of classification, I want to do this exercise with you guys. So these are actual emails that I have received in my inbox. These are actually from like last fall, but they're still pretty good to show here. So these are real emails that I received. And so I'd like you guys to guess, like, I'd like you to assign a category, predict what the category is for each of these. Is each email spam or is it not spam? So what do you guys think about this first one, let's say? Do you guys think the first one is spam? Okay. No. How about the second one? Okay. How about the third one? Most people saying yes. No. And how about the last one? Yeah, that's a good one. So go said maybe. Okay. So the first one is actually not spam. So I actually did submit a Wells Fargo payment that day. The second one, unfortunately, is spam. So I wish this wasn't the case, but it is. And the third one actually seems like it probably is spam, but it actually wasn't spam. So this was actually a friend of mine who, from my like graduate program, who I hadn't talked to in a long time, and we just did like a product launch for my company that day. So she kind of reached out, but this is actually real, but it definitely looks really spammy. And then the last one was actually spam for me because I don't shop for handbags at Michael Kors, but you know, I think it depends. So the last one probably kind of depends on the context of who's getting the email to some extent. Um, but you know, you could imagine someone else's inbox. This could be a very normal, expected thing. So you know, it just depends. But it's interesting. Like you guys were able to guess most of these, you know, pretty reasonably well. Um, and you know, there's probably some patterns you looked at, right, to pick up on that. But really, all you had was just this text. Like this is all you had to predict from. You had incomplete information. You didn't know everything about this email. You don't know everything about me, but you were still able to make pretty good predictions on what the category is going to be just by looking at the text. You know, maybe this third one in particular, you guys saw like a lot of exclamation marks. You're like, okay, that probably seems like it might be spam. The second one was like, okay, that number amount is like really large. It seems kind of crazy. So, you know, you guys use some sort of rules, but maybe not explicitly. And so that's just kind of how you make predictions. So that's pretty cool. And so that's one example of it. And so today, Google has really good spam filters. So if you go into like Gmail, like the spam filters are like pretty spot on. Sometimes they get it wrong, but they do a pretty good job. And so they're able to predict this using a statistical model. And so we'll talk about like some types of models that can be used to do that, to basically automate that. So instead of having like a person read all my emails, which is like really creepy, we can just have an algorithm do it, and then you can filter the email for me. So this brings us to the concept of a machine learning algorithm. And so again, I'm introducing it here today in the context of classification, but there's machine learning algorithms that do regression as well. So we're just kind of introducing it now because now you've seen like one way to do regression. But again, machine learning algorithm works in numerical and categorical, regression and classification, works for both. But at the end of the day, what is a machine learning algorithm? So it's a mathematical model that's calculated based on sample data. So you take some sample of data, some individuals, where you can observe all of the properties, all of the attributes, and the outcome that you care about. So you observe both of those things for all those people. That's your kind of sample data. This is typically called training data in the context of machine learning, but it's just sample data that we've already been talking about. So nothing different really there. And then this mathematical model makes predictions on kind of new individuals without being explicitly performed, or especially being programmed to perform the task. So what that means is it's not trying to make some rules-based decisions. It's not saying like, okay, if this email has 10 exclamation marks or it has, you know, 4 zeros back to back or whatever it is, 10 zeros back to back. It's not doing some explicit based set of rules. It's just using the sample data and like what associations it finds between attributes and the outcome. And then based on that, it mathematically determines that like, okay, if I come in and see this new individual, they have these certain attributes. It's statistically likely that the outcome is going to be whatever because our sample data shows that people with those kinds of attributes have certain kind of outcome. So that's the basic idea of how a machine learning model works, or machine learning algorithm works. And so now coming back to classification, this is something that we're going to do in the context of predicting something that is categorical, just like what you just did. So just to show you a few more examples to kind of drive it home. So obviously you have like the spam case. That's a really common example here. Another cool example that I want to show you guys is in self-driving cars. So classification is used all the time. So I did a lot of work on this at Tesla. And basically, what you're seeing here is this is like an image, a camera like shooting out of the front of the car, and it's seeing the world around it. And so if I zoom in a little bit, you'll be able to see here, it's picking up this bus, and at the top it says vehicle. And it's picking up a person standing on the sidewalk, and it says P, so like pedestrian. So it's classifying what category each object is in the scene. And so this is a really, really important task in self-driving because you need to understand the scenery around you. And so classification is used there. And then another common case is on Amazon. So if you do shopping on Amazon, you'll see product suggestions. So product suggestions, those are categories because there's millions of products out in the world, but it's not numerical. Like you can't really compare like one product is greater than another necessarily. So products are just like categories. Every single product is its own category. So that's another type of classification. This was an actual recommendation I got. So I went on a trip like a year ago and I bought some like water shoes, and then Amazon just started recommending like more water shoes and like outdoor gear and stuff like that. So it was kind of funny. But yeah, Amazon's a little bit iffy. I don't know if it works that well, but it works well sometimes. But they try to pick items for you based on what you want to do. So those are some examples. So let's also take a look now at some actual examples in the data and then see like how we might try to actually classify things there. So in this particular case, we're going to read in this data set, which actually contains patients from a hospital. And so every row in this table is going to have the patient. And so there's all kinds of attributes that we observe about the patients. So we know their age, their blood pressure, specific gravity, all this kind of stuff. And they've gone through some lab tests, let's say. So we have not only like basic information about them, but we have some like really specific information here, like sodium, potassium, like hemoglobin. Like you would have had to do some blood tests to get this kind of stuff. So it's like really, really detailed information about them. So anyway, so we have all this information about somebody. And then over here at the end, we have this column that says class. So class is going to be the category that we're trying to predict. It's kind of why it's called classification. It's kind of the class. In this case, it's just going to be two classes. So it's like either 0 or 1. And so this particular data set is trying to look at patients who may have chronic kidney disease. So it says CKD. So the class basically says 0 if you don't have the disease, and then 1 if you do have the disease. And so if we just want to take a look at what the data breakdown looks like, we can do ckd.group class. And so that'll just break down the data. So most of the people, most of the patients in this data set don't have the disease, but 43 of them do have the disease. So we can just see kind of the breakdown here. And so what thing we might want to do is try to predict, if some new person comes in, and we might want to try to understand whether they had a disease or not. And maybe it's really expensive to run like all these tests because there's a lot of variables here. Maybe you have to run like 4 different tests to gather all this information and then finally determine like what, some subject expert had to come in like, and some kidney expert had to come in and like look at the lab results of all this data and then determine like, okay, yeah, I think they have the disease for sure. I think this person doesn't have the disease. So that's really expensive to do. And so what you might want to do is say, okay, what if we could just take like a few variables, just do a really preliminary, easy like blood test, nothing fancy, and then just try to see if we can predict whether they are going to have the disease or not without having to do all those additional tests. So again, it's the same concept. With limited information, can we make a prediction that's like almost as good as what an expert would do if they had like a lot of data in front of them? And so let's take just like two variables, for example, that are like pretty standard to collect in a blood test. So white blood cell count and glucose. And then what we're going to do is we're going to visualize the individuals along both of these axes, but we're also going to color the scatter plot based on whether the person has a disease or not. So in this case, if you're blue, that means you don't have the disease. And then if you're orange, or gold, I should say, if you're gold, then you do have the disease. And so we can kind of see the difference here. So we have white blood cell count in the bottom, we have glucose up here. And so the question for you guys is, let's say a new patient comes in and they have a white blood cell count of 15,000 and a glucose count of 200. So where my cursor is. So what would you guys think? Like, do you think they had the disease or they don't have the disease? Right, they had the disease. And why did you guys think that? Those of you who said yes. Yeah, so there's gold, someone said machine learning. Yeah, so the gold points basically, right? So there's gold points nearby. That's kind of why. And blue points are nearby. And then what if somebody had like 7,500 and a glucose of like 500? So like over here, right? Then what would you guess? Like would they have the disease or not if they're at the cursor? Right? Yeah, so they're not, right? So in this case, a lot more blue points, things like that. Now, what if I'm over, let me zoom in a little bit. Oh, that didn't work at all. Okay, shoot. What if, there we go. What if I'm like around here? So maybe you have like 7,500 on white blood cell count, and then my glucose is like 125. So I'm like right around here. Then what would you guess? Ah, that's a good answer. Need more tests. I like that. Yeah, so it's like, you might have it, might not, but maybe you're not as confident about it, right? And so you can kind of see like, seems like you can kind of determine some sort of rules, at least, sort of. But that's cool. So you guys are kind of have the intuition for kind of finding what could be a good machine learning algorithm potentially here. So now let's try another set of variables. So look at hemoglobin and glucose. So hemoglobin is down here, and then we have glucose up here. And so in this case, what's interesting is this separation between the two seems to be even clearer. So in this case, we have like this blue cluster all right here, and then we have this gold set of points all out here. So it seems like if you use these two variables, you can make a really clear distinction. Like, there's very little ambiguity. Once you get like up here around this area, maybe there's kind of like a gray area, you're not sure. But there's definitely seems to be like a really clear separation between the two. So that's kind of interesting. And then you'll see this a lot in data science. Like there's going to be some variables where you have a clear separation in your classes, and then some where you don't. And so it just kind of varies. But maybe these two variables are better to use if you had to do like a really simple test and only like look at a couple things. This might be what you want to do. And so let's say that now we have this and we wanted to create a mathematical model to predict like a class of somebody who's new. So one way we could do this is we could try to find this kind of area here where you have that transition between like blue and gold. So if I put my cursor along this thing, looks like I need to basically figure out what is the maximum glucose level for everybody who's blue. If I can figure out what's the maximum glucose level for everybody who's blue, that's going to be roughly around here. So right, glucose is on this axis. So if I can figure out what the maximum glucose is, it seems like that's going to give me that line. And then if I want to figure out this line, I need to basically just find the minimum hemoglobin from everybody who's blue as well. So everybody who doesn't have a disease. So if I can find those two things, I can probably come up with a pretty decent rule here. And so that's exactly what we're going to do here. So we'll find the max glucose for people who are 0, don't have the disease, and minimum hemoglobin. So we'll run this here. And then what we can do is, now that we have the minimum and the max for these two axes, then what we can do is we can create a rule here and say that let's make this function called classify. And then all it's going to do basically is going to say, give me the hemoglobin for somebody and their glucose, and then it's going to predict whether they have a disease or not. And how is it going to do that? It's going to do basically the same thing we just did by kind of eyeballing it. So if the hemoglobin is less than this minimum glucose for 0, so if it's on the left side of that, or the glucose is above this max glucose, so if it's above here, so if you're above this line or like to the left of this thing, then return 1, return that they do have a disease, because everything outside of that and to the left of that is gold. And then otherwise, just return 0. So this is going to be kind of our rule. So we can actually make this classifier now. And then we can actually try it out now. So let's try it out on somebody who has hemoglobin of 15 and glucose of 100. So that's going to be 15 would be over here, and then 100 is going to be right there. So basically like right there. And so let's try that out. And so we get 0, and that's what we would expect because it's like right in the middle of all this blue cluster of points. So it seems to work pretty well. And then let's try somebody who has hemoglobin of 10, which is over here, and then they have glucose of 300. So that's going to be over here and then go up to 300. So that's this point over here. So we can try it out there. And then we get a classification of 1. So that means that they do have the disease. So it seems to do like a pretty good job here. And we were able to make such a simple rule here just by kind of looking at the data, like eyeballing it basically. Well, it was data driven though, because we did find the max and the min. And then based on the max and the min, we decided to kind of make a prediction. So, in general, this probably won't work. And the main reason this doesn't really work in the real world is because it's really, really rare to find 2 variables like this where like the separation is so clear between the 2. Most of the time in the real world, you're going to see data like this, where the separation isn't so clear. And so maybe it's not as obvious how you would maybe find the difference between these 2 groups. So to show you another example of that, let's take a look at another set of data. And so in this data set, we have some banknotes, and we're trying to understand whether they're fraudulent or not. And so we won't worry too much about these numbers, but basically some like fraud experts have taken pictures of all of these notes, and they've generated some numbers from those pictures. And so we have these like 4 different numbers here. And then we have the class here, which is like whether the note is fraudulent or not. So it's going to be 0 if it's not fraudulent, and then 1 if it is. So let's take a look at kind of the distribution of the fraudulent or the class variable. So in this case, we have 762 banknotes that are not fraudulent, and then 610 that aren't. And so let's take a look at like 2 of these variables and see like what this looks like. So if you were to use these 2 variables, wavelet variance and wavelet kurtosis, don't worry too much about what that means, then we would see something like this. So it's kind of like a weird shaped pattern. There's like somewhat of a separation here, but then once you get down to this middle area here, it's like really hard to tell like what you should be predicting there. So it's like quite difficult to actually tell what you can do there. And then we can try another set of variables. So let's try wavelet skew and entropy. So here you start to see like a little bit more of a separation, like especially here in this area, there's like a really clear separation between these 2, minus maybe like some overlap here. But once you get up to the top left here, it's like really crazy, really hard to tell the difference. So most of the data in the real world is going to look like this typically. It's really rare that if you look at just 2 variables that you can find like a difference in categories so clearly. So this is typically what we're going to do. This is typically what data is going to look like. So what do you do in this case? Like, do you have any hope of doing an actual accurate prediction here? Well, the good thing is that in the real world, you're also typically going to observe multiple attributes. So you're not just going to have 2 attributes, you might have 3 or more. And so what's interesting is when you look at your data in 3 or more dimensions, it's really common that you can see a separation there. So even though there isn't a separation in 2 dimensions, you might see one in 3 dimensions. So for example, let's say I have my fist like this, right? So if I look at it, if I show it to you like this, it looks like there's no difference, there's no space between them, right? Because you're looking at things in 2 dimensions. I'm like flattening it together. But if I were to rotate this out so you could see it in 3 dimensions, you'd actually be able to see that, oh, there actually is a space there. And so you could imagine something similar with these 2 as well. If there's a way where maybe in 3 dimensions, these 2 like curve shaped things are actually like separated like that, that would mean that there is a separation, but I need an additional variable to see that. And so let's actually do that. This is gonna be kind of crazy. Let's actually do this. Let's visualize in 3 dimensions. So we're gonna do wavelet skew, wavelet variance, which is the first one that we did, and wavelet kurtosis, which is the other first one that we did. So now if you do 3 dimensions, you see something like this. So in 2 dimensions, basically, you wouldn't be seeing this third axis here. You typically would only see like maybe this axis and this axis. And so if you're, let's say if you were standing like where my cursor is here, if you were standing here and looking at this cluster of points, they would look like they're just like overlapping and there's like no separation. But now that you're able to kind of add this third dimension, you can like separate them out and look at it like that. And so now you can see that, oh, there actually is a separation there. And so it's pretty cool that you can actually see this. And so, you know, in the real world, there's going to be a lot of situations like this where things actually separate really nicely if you have additional variables. Now, it's possible that maybe you wouldn't actually be able to separate it even in 3 dimensions. So maybe you have to go to like 4 dimensions or 5 dimensions. And that's really hard to visualize. I certainly don't know the best way to visualize that. So I wouldn't really worry too much about what that means. But the basic idea here is that when you go to higher dimensions, there's like things are more likely to be separated in higher dimensions. That's the main thing for you to keep in mind. And so basically what does that mean is the more variables you can observe, the higher chance you have of being able to separate these things. So that's the basic idea. So any questions about that? I know that's like kind of crazy. I see a lot of people just had their like mind blown, so that's good. But any questions about that? Can you do more dimensions? You can do more, but like visualizing it just gets like really really complicated, and it's not going to be intuitive as it is in 3 dimensions. I mean, we see the world in 3 dimensions, so that's kind of the best I think that most humans can visualize properly. It's just really hard to think about it beyond that, but you know, certainly you can do it in the math, and we'll explain that in the next lecture. Like how do you find a separation between things in like 5 dimensions? How is that even possible? We actually will go over that in the next lecture. But that's the basic idea. I just wanted to build the intuition there that like just because things aren't separated when you're looking at just 2 variables, if you look at additional variables, you might be able to find the separation. That's basically it. Cool. So finally, I just bring this to the last couple of slides, which is around classifiers. So the thing that you use to classify is called a classifier. It just has its own name because just in machine learning, it's really common to have like a mathematical model that does this. So they're called classifiers. And then the concept of like building a classifier using a statistical model, that's called training a classifier. So you'll hear this terminology a lot in machine learning. But the basic idea is you're just building that mathematical model using your sample data. So how can I use that sample data to create this classifier? And the basic setup of how a classifier actually works is you have attributes of some example that gets input into the classifier. So for example, you know, maybe you'd input like hemoglobin and glucose, put that into the classifier, and the classifier spits out a predicted label or predicted class. So that's kind of how the classifier works at a high level. And then how do we actually train this classifier? So the way it works is we have some data in the population. You know, you have your entire population that you want to study. Let's say you want to study all patients in the world. Obviously, you can't gather data from all the patients in the world. So you take a sample of them, you get some subset of them. So this is kind of the same thing we've already been doing. And then what you do is you have your sample and you observe like everything about them, all these attributes about them. And then you also observe their outcome, the class. This is really going to often be called labels. So class, labels, outcome, these are like all interchangeable, all the same thing. But in the context of machine learning, we tend to talk about labels. But basically that's the idea here. So every individual has like a label, an outcome, a class attached to them. And so it's really important that in this sample data that you get, you not only observe all these attributes about them, you also get to see the labels, because that's the thing you're trying to predict ultimately for some new individual. So once you have these 2 things, then what we actually end up doing is you split your data up into multiple pieces. And the reason that we do this is because if I go back here, if I take just this sample and labels, and if I create some classifier, some mathematical model from these, then I still need a way to assess how accurate they are, right? So let's say like I built some fancy model using all of my patient data from a hospital, and then now I want to apply it on some new patient who comes in, and I want to figure out whether they have the kidney disease or not. But I need to understand how well it's going to work on a new person. Um, and so if I need to assess how well it's actually going to work on a new person, I can't do that by just taking a bunch of new people because I don't know what their outcome is. I'd have to wait like maybe several months for all the test results to come back in order to figure out whether they have the disease or not. And I need to know right now whether this algorithm, this machine learning model is actually going to be effective. And so one thing we can do, which is a little bit clever, is we can say, well, hey, we have all this sample data right here where we know their attributes and we know their labels. So why don't we do something a little bit smart? Why don't we split our data into two sets? Let's split it into one set, which is the training set. That's the one that's going to be used to make the classifier. And then let's set aside some of the data as our test set. So our test set, we don't look at it. We just put it to the side. We don't do anything with it. It's just sitting there on the side. So we only use the training set to create our classifier. Now what we can do is, once we've built our classifier, we'll model the association between the attributes and the labels within this training set. Once we have that, then what we can do is, okay, I've built the classifier now. Now let's go run the classifier on my test set and then see the results. So I can run on the test set today and immediately I can tell you whether this thing is accurate or not, whether this machine learning model actually works well or not. And so the test set basically is only used at the very end to estimate the accuracy of your classifier. And so that's kind of the basic concept here in terms of how this is used. This is basic idea of all of machine learning really. And we're presenting it today in the context of classification, but it can also be used for regression too. So if you're trying to build some fancy model that predicts like some numerical value, you can follow the same exact process. You can sample some data, split it up into a training set and a test set, and then train your regression model on the training set, and then apply it to the test set to validate like how accurate it actually is. And so that's kind of the basic idea there. So you can do that either way. And so what we'll talk about next time specifically is a nearest neighbor classifier. And so nearest neighbor classifier is essentially what you guys were already doing intuitively in your mind. When I was putting my cursor over things and saying, what would you predict for this? You guys are basically saying, okay, there's a lot of gold dots around this point. I'm going to predict gold. Or there's a lot of blue dots around this point. I'm going to predict blue. You were essentially doing a nearest neighbor classifier in your head. And so nearest neighbor classifier just does that. So it basically says, okay, you've given me this point. I'm just going to find a few other people nearby in the training set and then figure out, what do most of them look like? If most of them are gold, I'm going to predict gold. Most of them are blue, I'm going to predict blue. So it's essentially what nearest neighbor classifier does. But other than that, the setup is exactly the same. So, there's attributes that are going to go into this classifier. It's going to predict a label on the other side. So that process is exactly the same. The only thing here is that this is a very specific way of generating those predicted labels. We also made our own classifier just earlier above, right? We made this one, if I go back to the notebook really quickly, we made this classifier right here, which decided the class just based on these boundaries. So it said, if you're above this threshold or to the left of this threshold, then you're gold. Otherwise, you're blue. That was our classifier. So we made a, data-driven classifier. Nearest neighbors is another way to do it, where it says, I don't really care about these thresholds here. I'm just going to find the point and then look at what's nearby, and then look at kind of who's the majority of the people nearby. Are they mostly gold? Or are they mostly blue? And whichever it is, that's what I'm going to pick. So that's what we're going to do, and we'll actually code that up in the next lecture. So it's going to be pretty exciting. So I'll actually show you how you can actually code up that classifier nearest neighbors, and then actually use it on a data set. Yeah, that's pretty much the last slide. So any questions about classification, classifiers, training set, test set, all that stuff? Cool. All right. I think I will stop the lecture there then, and then I'll stay on for any questions.